All right, so now we are ready for that big concept in calculus, the other half of the calculus learning that I've been talking about. Now we're looking at definite integrals, or that's the big beginning door of what integrals in general really means here. All right, so let's get to it. So I'm going to need to erase the title of our discussion topic here to put in a lot of details and explanation. And then after that, we're going to really learn and to find out what it is truly means to be a definite integral. Okay, and so I need to just maximize the board space I'm using. And I have to admit, the content being delivered in this video lecture here is specifically aimed or is specifically intended for calculus students of mine who are on track for business field, business majors, all kinds of business majors, or health and social sciences, because in the kind of practical work that you are doing out there. So any viewers of mine or any students of mine who are on track for business major, the kind of or the social and health sciences majors, the kind of work you're doing out there, you don't need all of the full details, but you just simply need the details that can practically apply immediately into your field right there. And so if you want to know more than what I deliver here in this video lectures, for example, for students who are studying, for calculus students of mine who are on track for engineering field or a formal math major or a physics major, all of those formal science major that heavily math related, then you need to find my other video lectures where I teach the exact same content right here, but I offer a much more the details that are designed, that are intended for your field to be apply. Okay, and so it just when we learn, we just need to look at the detail that apply directly to our field, to our need like that. Okay, so now before we can get ready into fully understanding what a definite integral is, let me wrap up a little bit and recap a couple points or remind a couple things back in our talks or back in our discussion topics about a Riemann sum right there. Okay, and so I brought up this picture that our function was an x squared, and it had this graph for us, and I only need this portion of the graph. I don't need the complete graph, and so I used that interval from 0 to 1 as our main interval. And I brought up that question that we want to find this shaded area completely inside of this bent graph right here. Okay, and so it's always the best starting out example that in my teaching experience that I felt. And so I started out introducing through the idea of using Riemann sum. And at this point, you got to be fluent that I also mentioned that Riemann sum is not necessarily an area. It's just a way, it's just a tool that we used to approximate an area. So at my start of this problem where I promoted, then I recommended to break that interval into 4 equal with the subintervals. And so we built a left endpoint intervals or right endpoint Riemann sum. Let's look at the left endpoint for now. So the first interval here, number 1, according to the left endpoint, and we have nothing else but just that rectangle of 0 height. And then we're moving on to rectangle number 2. Then our rectangle, see, left endpoint is here. And so when we evaluate into the picture, into the function, we have a height about like that. So the left endpoint decides the height of our sub-rectangle. And now we draw the rectangle over. Okay, so there's my rectangle number 2. Okay, and then on third interval, the left endpoint is here. And so I got that. Left endpoint is the point to decide the height for my third rectangle. And that's how I had this. And again, you shouldn't be surprised about how I've got this, because I'm assuming that anyone viewing this video has arrived here after viewing my earlier video lectures about the Riemann sum. And so now the last interval here, I'm picking the left endpoint. And that's the idea. That was the idea that we used for in our earlier lecture. And here I'm just recapping it. And then same picture, maybe let me leave that picture here and head out on the other board, and same picture. Okay, and from the interval, same interval again, from 0 to 1, I stay with 4 subintervals again, but on each of the intervals here, I also show that we can, on the other choice, we can choose as the right endpoint. So on first interval here, right endpoint is here, and that decides our height. So we had a picture like this, okay? Even though not too high, but it's a recognizable rectangle there. Okay, and then on the second interval, subinterval, we chose the right endpoint because see the rule here is the right Riemann sum. So this is R4, okay, and we had a rectangle like that, and this is just a way to envision or to visualize the work right there. And then that one here is an interval where the height is decided by the right endpoint. Okay, so we have another rectangle. And then the fourth interval, specifically in this case right here, the right endpoint is here, decided by, the height of that last interval is this high right here, decided by our right endpoint, which is also the last point of our interval. Okay, and it's right there. Okay. And so we were summing up. That's why it was called a Riemann sum. Okay, but now in the end, what I pointed out a couple of times already throughout our talks in the Riemann sum, and maybe it's also best that I can bring it up in the picture here. So here's that graph that you were seeing on the board. So with this graph, the interval from 0 to 1 is here. I put the 2 tick marks right there. This is the interval. 0 is here, 1 is there, and allow me to skip the numerical label. And now these are the partition points, just like that how I drew on the board just earlier. Now with really good precision with decimals. And so left Riemann sum created these pictures for us, okay, these little sub-rectangles. And so the areas, I discussed this back in our talk about the Riemann sums, that the area was, the accumulation of these rectangle areas were a little under the actual area that we need due to these white spaces here. Okay, and now let me hide away the left Riemann sum. The picture created by the left Riemann sum and put on the picture that was created by the right Riemann sum. So just like what I drew on the board, these are our rectangle, but the height of the rectangle in each subinterval here is determined by is decided by the right endpoint substituted into the function. See, so the first rectangle here, it wasn't too high, but at least I can see that the height here is perfectly consistent with the right endpoint on the first interval plugged into our function, being the red curve right here. And so that's how we have all of these rectangles created by choosing the right endpoint. But in the end, the trade-off for this is this approximate is still not good either, because it's quite an overestimate. It's an overestimate due to all these excessive amount of blue area above our curve like that. Okay, and so I also talked about back in our discussion about Riemann sum that we can improve. There are ways, and the only way to improve is to improve the precision. Now let's get back to the left Riemann sum right here. The only way to improve and to shrink down all of these white spaces here is to increase the number of rectangles. So I can increase that to 16 rectangles, for example. So pause the video if you have to quickly count. And so here I have 16 sub-rectangles, 16 sub-intervals that consequently produce 16 sub-rectangles. And so in that way, I already, you can see that the total accumulated area of the rectangles here came to a lot closer than the actual area we're looking at. And then the amount of white spaces here together cumulatively has shrunk. Okay, but then I'm not happy with this. We still see a difference between the approximate and the actual area. So I'm going to increase more. I'm going to change to 40. I'm going to keep increasing. And then I also back at our talk about the Riemann sums, and I started to put in your curiosity this question. Think about what happens when in the same interval, but you keep trying to fit more sub-intervals in it. See, this is what I'm doing right here. Same interval from 0 to 1, but I'm trying to keep, I keep fitting more equal with sub-rectangles in it or sub-intervals in it. So think about what's consequently happening to each of the intervals width here. Okay, and hopefully you already had an answer at this point when you have arrived. But now I'm still not happy with 40 the sub-intervals, because there are still these visible white spaces here. That means we're still a little under the actual area. And so now I'm going to increase to, how about to 150. And so now the area looks all the accumulation of of all the rectangle areas looks so fine, and it looks, I mean, through I'm only standing about 2 feet away from my computer screen, and I literally cannot see the difference anymore. So now the idea now is that the idea I'm doing here in the picture here is equivalent to a fact that, okay, so now let me get back to the picture. On my board here, so we've learned through Riemann sum that we use OR-N. We use OR-N, and the setup is following. And here specifically, we started out with OR4, and so we use LN here actually on this board. Left endpoint, a Riemann sum with 4 subintervals here, but generally we use the OR-N at some finite number of subintervals. And finite means, it's a big word, but finite means something countable. Okay? And so that was the general Riemann sum that I generalized at somewhere near the end of our lecture about the Riemann sums. We picked on any interval I, we picked the left endpoint, and then substitute that into the function value, then multiply with the delta x, and then the reason I wrote and then I erased because I want you to follow the order. We got to get all of these multiplications, all of these products nailed down in each of your rectangle, and then we're going to sum up all of the rectangle, all in that operation here, all the way from first rectangle, first interval to the last interval n right there. So that's what we did, and generally this gave us, that gets straight into the definition of our understanding of what a Riemann sum is, and specifically this is a left Riemann sum. But now the picture I was showing on screen earlier, that we just stopping at 40 subintervals or n equals 40 did not give us a happily satisfying answer. Stopping at 100 was not happy enough. Stopping at 150 in the end, if we stop at any of the finite count for the number of subintervals, we're still going to have a little bit. Maybe our eyes cannot see it, but the computers can still see it. So the idea now, so the picture I was describing, that we keep letting the amount of rectangles, we keep having more and more rectangles in here, or we keep breaking our same intervals into more subintervals. So we keep increasing the number of subintervals here. I now start using a term increasing and increasing. I hope that brings up a concept that you have learned throughout your earlier calculus learning time. That's work you have seen as a demonstration on the computer screen is equivalent to this work, the following operation, from where our, well, currently the left Riemann sum, from where our current left Riemann sum is. Okay, and it's a sum from the first rectangle or first subinterval to the last subinterval. But now the work I was demonstrating on the board there is equivalent logically to, we want to keep increasing. So I'm taking the limits. Allowing n to keep growing infinitely large, allowing n to keep getting more and more and more, keep having more n and more n. Okay, so now let me write it down in a bigger space right here so you can have a real nice clear view of that. So it's starting out with a Riemann sum with some finite n count for your n number of subintervals. And in this board here I'm using specifically the left Riemann sum with n subintervals. But now, unhappy with any particular finite count, we're going to really need to achieve. So to achieve the best exact area inside of this curve here, we desire to apply the limit operation on that. Okay, we desire to apply the limit operation on that. And so on the right, on the left Riemann sum, we can, you see the work to achieve our best area, our most precise area inside the curve here from that interval between 0 and 1 right there is truly taking the limits, letting n grow to infinity. Okay, so what about the right endpoint? What about for the right endpoint Riemann sum right here? See, this was R4. So as a reminder, Rn was specifically on each subinterval. I'm going to pick a point on each I interval, and I'm going to pick the right endpoint. And then the operation of the Riemann sum set, I need to substitute that right endpoint into the function and multiply with the delta x. And then we're going to sum up all of these products right here from the first rectangle or the first interval to the last interval. That's the general idea or that's the familiar definition of our right endpoint or right Riemann sum, with generally at some finite n counts of the number of subintervals. But now let me get on the picture. All right, so I apologize for taking a little bit of time to prepare a picture here. But so back on that blank, starting from scratch picture right here, here's our interval from 0 to 1. And I already had that broken down into 4 equal width subintervals. And so now with the right Riemann sum, this is what the picture looked like. And so we had, as I discussed earlier, we had overestimates here because these are the excessive amount of blue areas that stayed above our curve. But now, so if we are not, so now because we are not happy with this overestimate right here, I am going to increase from 4 to a higher number. How about 16 sub-rectangles or 16 subintervals? And you can pause the video to count here. And the Desmos can produce such a beautiful looking graph for us right here. So the amount of overestimates has shrunk. But in the end, we still have a visible amount of overestimates here. And so I'm not happy with that. And so again, I am going to increase. So now I'm going to increase to about 100. Okay, and so now 100. Then it's starting. It has already become so much of a challenge to see, but I can still see a little bit of a coarseness here. Okay, some that indicating we still have some overcount here. Okay, and so now that means I'm still not happy with this with 100 intervals. Sub-intervals in between our interval from 0 to 1. And so that means there's still some overcount. So I'm going to, but you can see now that as we keep increasing our number of sub-intervals, then the area, the accumulation of the Riemann sum keep getting better and getting closer to our actual area. And along the way, keep thinking about what's the consequence, what that consequence of producing more sub-intervals within a limited interval like this will bring for us. Okay, because you can see now that what's happening to the width here. Okay, now I'm going to change to about 180 subintervals. So now I'm standing only not even 2 feet away from my computer screen, and I can't even tell the difference between the area shaded in blue and the actual area, the trap between the curve here and the x-axis any longer. So that means the idea now again is that we keep getting better answer, we keep getting better approximates of the real area as we increase, as we are increasing the number of sub-intervals or sub-rectangles. And so this demonstration here I'm doing on the computer screen is again equivalent to the fact that with our current Riemann sum defined for a finite n count of subintervals. Now to achieve, if we want to use, and remember I explained hopefully clearly enough that at the end of our talk about the Riemann sum, then Riemann sum is only a tool that we use to approximate an area when we can. Okay, but it's not always tied down. So a Riemann sum is one operation on its own right here. But in the end, this Riemann sum, if we apply that to find the area here, then we can do this work right here on our current right endpoint Riemann sum with n subintervals. But now, if we use this as a tool to approximate our area, then we can get the exact area by applying another additional operation on that, the limit operation, that we allow n to grow to infinity. We want to fit more rectangles. We want to fit more subintervals into the same space between 0 and 1. Okay, and so that's the idea. We take a limit. So we set up that Riemann sum for n intervals, and then we're going to take the limits allowing n to grow to infinity. Okay, and so now that's just an illustration of the concept right there through the example of finding area. So in the end, if we strictly stay with the Riemann sum, so now I'm going to clear away the area picture here. All right. And so just simply as a Riemann sum. Just simply as a Riemann sum. How about left Riemann sum? Okay. Left Riemann sum with n subintervals. And we're summing all of that from the beginning, from the first interval to the last interval, just as simply or as purely as a Riemann sum. We can always apply the limits operation on top of that by letting n grow to infinity. And then so similarly, and again I'm saying that we're departing from the area problem. I already erased the area picture. But just as a Riemann sum, a right Riemann sum problem, summing up all of the products that function output at the right endpoint on each interval and multiply with delta x. Okay, and then we're summing up all of those products from first interval to the last interval. This is the right endpoint or Rn right here. But now on top of that, we can always define a more advanced version. So this is not only a Riemann sum, it's a Riemann sum with the limits on top of that. It's a Riemann sum where we want the number of subintervals here keep increasing and keep increasing. Okay, and so ultimately I came to that general definition of a general Riemann sum. So generally, either right endpoint or left endpoint is simply just a point in any specific interval that I chose. That's why I call it, it's a C point. And so this C point represented, it could be a right or it could be a left. Okay, and so now, so generally as a Riemann sum, that's how it happens. We're summing up all the way from first interval to the last interval. And so on this Riemann sum, this general Riemann sum, we can also apply the limits concept on top of that. This limits by letting n grow to infinity. Okay, and so now, ladies and gentlemen, we have now come to the following definition. So let me one more time bring up the area picture. Okay, so for this function, specifically in our example that I brought up, x squared, we got this graph right here, okay, and from 0 to 1, but now we broke it down to so many x and the y-axis, and we broke that down into so many sub-rectangles in there to the point that I don't even want to draw the rectangles in here anymore. I'm just talking about the area that supposedly, if we're shading inside of this area in between the curve and the x-axis from between 0 and 1. And so now, if we are using generally the left endpoint rule, for example, okay, so this is the left endpoint Riemann sum, and now we're letting the limits, the number of n, to grow to infinity. If we're doing that, now it's time to bring out that impact I started to put in your curiosity a little while ago already. Now really bring out that understanding of yours right here. If we increase the number of n here to infinity, meaning same intervals, but I keep breaking it down to more and more and more and more subintervals, then each interval width, see if you agree with me now, each interval width has to get smaller, and get smaller, and get smaller. Look at my picture demonstration again. This here is the right endpoint. Let me quickly switch to the left endpoint here. Okay, left Riemann sum. We started out with, okay, now you can see that through the demonstration here. Right now I stay with 10, and then if we increase to more, okay, same total intervals width, but if we as we increase more subintervals, as we desire more subintervals, each interval's width here from here to here is becoming narrower and narrower. Okay, and so it's so narrow to the point that eventually at a certain point when our number of subintervals reach high enough, then we can't see the difference between left end and right end anymore. And so here's the idea. And I started using that term accumulation a little while back already. And so a Riemann sum is accumulation of you see, a height with a width, a height with a width, right? It's completely fine to think of that as a picture of the area. But now as we increasing the number of rectangles, then the width of each rectangle becomes so thin and so thin to the point that, see, if I'm saying that here's my rectangle, I'm not lying. Just a pencil stripe like this has a thickness already. That's dx, but getting infinitesimally small, okay? And then, see, because if the delta x is big, if we still have a rectangle like that, and that's big, but I'm talking about as we infinitely increase our number of n right here, then the rectangle gets so thin to the point now that only one pencil stroke like that has its own width, and that width there supposedly delta x, and then the height here is supposedly some hard to recognize left endpoint, because you see I stand right here with that. I can't see where the left endpoint and where the right endpoint on that pencil stroke is, but supposedly there's an infinitesimally small difference between that, okay? And so now, but think about it, we're accumulating that area of the stripe, okay? And so there's another stripe next to it, making the area thicker. The area next to it making the area thicker, and the area next to it accumulating it up, making it thicker. But each area here, the height of the stripe is being governed, being decided by where the function is at. And so, thus consequently, so when the stripes become that thin, each of your rectangle become that thin, then the delta x here will no longer be, I mean, it comes to something else. We won't use that as a delta x, because so delta x is for something big. But now when it gets so small like this, where it's just like a one pencil stroke like this can be enough to represent how thin that is. So we call that delta x there, the delta x here become the dx right here. Okay, see, d is for difference, but now infinitesimally small difference. Instead of something like this, where it's still big, something we can still recognize. So delta x is something we can still recognize, but when we have that many, like an unlimited count of number of subintervals, then d delta x becomes a dx. And when it gets to that many subintervals, then see, left endpoint and right endpoint really come to just one. Just like when I'm demonstrating here on the pencil stripe right here. I can't really tell, even though I can't really tell, even though I stand right here at the board, left endpoint and right endpoint. It all becomes just one point x, and then the height of the stripe is the function at that x value. So now I'm looking at f of x times dx. Okay, so x here is just, it could be left endpoint, it could be right endpoint, because it comes so close. And that's also the reason why when I first introduced about the Riemann sum, I said when it started out taking that route as a left endpoint rule or as a right endpoint rule is simply as a choice, because now ultimately at the level where you need to take the limits, letting n, the number of subintervals, increase to infinity, then it all becomes just left endpoint or right endpoint get to 1. Okay, and so now see, that represents the height. So how about specifically for this particular example, then you see the height is the x squared. That's the function. So at any point, left endpoint or right endpoint, it all just comes to an x value at that instance. Okay, that instance at the x. So left endpoint or right endpoint meet the same. The height is your function x squared, and then the dx now is the infinitesimal version of that delta x. And now we're summing up. I started using that term a little while ago, but now I start emphasizing it a lot more. A sum is accumulation. A sum is accumulation. So now, ladies and gentlemen, I introduce for you, when we reach to infinitely many, if it happens, when we reach to infinitely many subrectangles, subintervals inside a limited interval like this, the sum there becomes accumulation. So now it's this S-like symbol. It's accumulation. Okay, we sum up, we're accumulating up all the stripes. Each stripe has height x squared with a width infinitesimally small dx right here. And all of those stripes we're accumulating up from 0 to 1. This is now called for this specific problem, it's called the definite. This is called the definite integral. The definite integral. right, of the function f of x, specifically in this example, x squared, okay, over the interval from 0 to 1. See, 0 to 1 is we call this is the lower limit of the definite integral, and this is the upper limit of the definite integral. It's just a little bit of a side talk here, but anyone deserves to understand this. Even in our daily language that we use, the English that we use, what does the word integrate mean? What does the word integrate mean? Think about that for a moment. Okay? Doesn't integrate means we're bringing things together? Accumulating things? That's what it is. That's why we call it's an integral. It's an integral. We're accumulating, we are putting all of these, we integrate all of these little stripes together from one stripe, but we integrate infinitely many stripes to get what we want to achieve, the area, the total accumulated area inside of that. And so now we don't need a special formula. That's what we do. Okay? And so now, same way. See, I used the left endpoint on this, but even with the right endpoint as a Riemann sum, okay, for right endpoint on any subintervals, right endpoint with the delta x, and then we are now letting the number of subintervals increase to infinity. That again will become just one picture. So that's why I don't need to draw. There's no way to draw another picture like this to represent an infinite number of subintervals for that where we pick the right endpoint. So it's the same picture because right endpoint and left endpoint, as we increase to infinite, to having infinitely many subintervals here, then left endpoint and right endpoint on any interval. See, a stripe like this, there's already an interval. It's just our eyes cannot see it. So an interval like that, left endpoint and right endpoint comes together. And so when we take to that, or when we're doing this route, it's all going to bring it down to this version. The delta x becomes the dx, the infinitesimally small dx. And then the left endpoint or right endpoint evaluated into the function now becomes the x squared. Because at any instance we have a height. Doesn't matter left endpoint or right endpoint anymore. It's a height. And the height here is decided by the function setting, the definition of our function. And then we're accumulating. It's all about accumulation. So we're accumulating all of those stripes from our beginning point of the interval to the ending point. So that's why it's a definite integral. So this right Riemann sum, or the left Riemann sum, as we let the limits of n goes to infinity, both of these becomes the definite integral. And in this specific case here, the function is x squared. So the definite integral on x squared, right? That's of the function x squared over the interval from 0 to 1. Okay, so now in that way, let me get back to my other board, and now we are ready for a general definition of what a definite integral is. All right, so now, ladies and gentlemen, as a definition, and I have to write it down carefully this time. It's a definition for definite integrals. So this symbol is called a definite integral. Okay, from a to b. That's how we say it. The definite integral of a function f of x in respect to x from a to b. So definite integral of f of x equals, as a definition, it's really equal to any of the general Riemann sum. A Riemann sum, how about the Riemann sum taking generally any chosen point in a specific given interval, multiply with the width dx, and then of course summing up, accumulating up all the way from first rectangle to first subinterval to the last subinterval. But on top of that, we take that as a limit. We take that sum as a limit, letting n grow to infinity. This is the ultimate definition of an integral, definite integral from a to b. And so now, and of course, this is provided that f of x is defined. It has values and continuous, right, on the interval from a to b. Okay, and so in that way, that's the definition to put in a box. That's what it means. That's what it is. Okay, but now just the way we call it, the way we say it, this whole package as a symbol over here says, and so you can see that the dx here this time does really mean times. It's a product. We got stripes multiplied with infinitesimally small the thickness. And I start using that term thickness because that's what it is. Now it's just, instead of talking about a wide, big, the recognizable, the width right here, now it's when it becomes so thin, it's just the thickness of a stripe right there. Okay? But in the end, this is called, the whole package here is called this is the definite integral. Okay? The definite integral of the function f of x, okay, over the interval from a to b. So a is the start of the interval. We always put it at the bottom. Okay, we always put it at the bottom of our integral sign like that. And then the ending of our interval, the ending of our accumulation. So that's sort of like we're accumulating from start at a and ending at b like that. So the ending point is always at b like that. Okay, so the ending point of the intervals always have to be on top. But this here is just a name, how we say it. But the true definition for any continuous function and defined on an interval from a to b, then the interval, I mean the definite integral of that function in respect to x, right? Or just formally the definite integral of function f of x over that interval from a to b is simply just, it's the Riemann sum generally. And then on top of that, we have to allow the number of n gets to infinity. Okay? And so if any of you need to take notes, then I can just simply erase all of these extra writing because I wrote that down for careful purpose. But of course, any of our function that we're learning at start, they're all continuous function, mostly. We won't learn to handle the integral for this continuous function not until like anyone has decided to go into a real formal math major course where we will learn a more advanced technique to find definite integrals there for the kind of complicated function. But here mostly we assume our functions are continuous and be defined. And so in that way, this is your core definition in case you need to take notes. Okay? And so that's why consequently, see, now I'm talking about just a chosen point. It could be the left endpoint, could be a right endpoint. And so consequently from this definition, now I'm going to need to go back to my other board right there. And so right out from that definition, then we can also understand that. So it's also true, once we had our definition of what a definite integral is, then it's also true that now if we're taking specifically the left endpoint, the left Riemann sum, if we're approaching the left, using the left Riemann sum and apply on top of that limits as n go to infinity, okay, this is also letting exactly into the definite integral of our function f of x with the infinitesimal thickness dx right there, or just simply the definite integral of our function f of x over that interval from a to b. Of course, I'm still in the same assumed interval with the general definition. And so So it's also true as another truth here that the right endpoint or the right Riemann sum will also arrive. See, this is the right Riemann sum. And now applying the limits concept of that on top of that. Okay, for I from 1 to n, the right endpoint, the right Riemann sum also arrive at the exact same definite integral. The definite integral of the function f of x over the interval from a to b. Okay, and so now I also need to emphasize it. I mentioned this, but now I just want to emphasize the relationship or what connects between the f of x symbol and the dx here is indeed a real multiplication. So dx, now you can think of that as the infinitesimally small thickness of a pencil stripe that you're drawing on your picture right there. All right, so I'm going to get back to my other board. So we now came to that ultimate definition. But then, good news for any one of us, and that's why, as I mentioned earlier, the content for this particular video is delivered to aim at students or viewers who are on track to business field or the social and health sciences, or so your actual career later on won't require you to know how to derive all these crazy things like that. So yes, you need to know to appreciate how much the mathematicians in the past have come up with this idea for you. But the good news for any one of us here learning, and specifically I'm communicating with students who are on track for business major or social health and social sciences, the work seems pretty deadly. We got a sum. That's the first thing. A lot of terms already to handle. And on top of that, we got to take a limit. Okay? Good news for us. We will never have, for all kinds of applications out there, I only show you what it means here for having a definite integral. But then right after this, I'm going to show you an amazing method, that get us complete any of the definite integral problem without any limits work at all. Okay? So that means, of course, if any of my students are on track for a formal math major, they are required to actually know, at least up until these modern day, I'm talking about the formal math major or the physicist. I mean the students who are on their way to become physicists or engineering, then they are required to know at least a few problems, how they have to work through the limits to get to the actual answer of that. Because an integral is a limit, the limits of the Riemann sum, where we keep letting the number of n's get bigger. That's the ultimate understanding. Okay, but for our kind of class here, for our kind of work and application we will be doing out there in your field in the future, you don't need to go through all that deadly limits work. So let's leave that for students who need to know how we go through the limits. See me with my other video lectures where I deliver the contents there for the students who are in math major formally. But here, allow me to make that splitting point to specifically go in the route for students who are on track for business math and social and sciences, social and health sciences. Okay, so we just know that as a goal here, we want to do accumulation. An integral, a definite integral, or for short, an integral is accumulation. We're summing up all of the stripes. Each of the stripe has a height, the f of x, and then it has a thickness dx right here, and we're summing it up, we're accumulating up. That's what the symbol is for, like an S shape, like an advanced S shape. And we're summing up, we're accumulating up all the way from A to B. That's what it is. All right, but now I guarantee you, for our kind of class, for the rest of your learning time with me here, you don't need to do any limit work. So let's see what's that fabulous tool that I was talking about can do for you. Okay, so now, sadly, I'm going to have to erase this definition because my board space here is so limited. All right, so now, ladies and gentlemen, the fabulous tool that I was talking about lately is regarded as the fundamental. Allow me to reserve the traditional name right here, the fundamental theorem of calculus. Many mathematicians, many professors, including me, refer to this fundamental theorem of calculus as this is the FTC here. That's short for fundamental theorem of calculus. This is all to be credited to Isaac Newton. So it was really developed by Isaac Newton right here and formalized all that idea here. I just want to, at some point have my students appreciate how much the work of the past mathematicians have done for us, and it brings tremendous applications for our lives in these days. And this thing here, over 300 years ago, came out from Isaac Newton. That it was just a theorem he has proven. But then, in these days, surprisingly how much it has carried into our daily work. In any field, you won't get away from the fundamental theorem of calculus. So, this is what it is. So now, I'm going to start out with our theorem by just stating a couple preliminary statements here. Let f of x, okay, be a function, okay, that is defined and continuous. And of course, I bring up the version of this definition for assuming that our kind of functions we're working here are all definite, or all defined and continuous. So it's simple enough. And we will learn the more advanced version if any of you arrive at a higher course in advanced calculus and see me there. Okay? But here we just need to focus on the simple side of that. So, as a preliminary, so f of x be a function that's defined on that interval and also continuous anywhere inside of that interval. That's just the critical requirements we need right there. And so now, once we have that satisfaction, that requirement, then, see, recall again. Start putting in your mind, anytime now you see this symbol, it means it's accumulation. It's accumulation of infinitely many stripes from beginning point A to the ending point in your interval from A to B. Each stripe has, has height, f of x, and thickness, dx. That's what we do, and we see, and it's a product between the height, and the height here could also be a negative height. I'll get more detail into that later, but it's just simply each one, that component here means it's a product between a function's height at any value x multiplied with the infinitesimally small thickness. And so that product's there, all of those are being accumulated from the beginning to the end. Keep thinking of that picture I've had on the computer screen or on the other board all over. Okay, I accumulate with the the pencil stripes like that. Okay, so this is that much work. Okay, but surprisingly, this is what Isaac Newton brought for us right here. This is what Isaac Newton brought for us. All that work, you no longer need to do limits. You bypass completely all the limits here. To get that exact answer, and I mean exact answer, find the capital F of x. The capital F of x. I'll clarify what that capital F of x is. But once we find the capital F of x, we're going to substitute the upper end of our interval into the capital F of x. And then we're going to subtract the same capital F of x there. I'm going to substitute in the value of our A point right there. All right, this is the result that's brought to us by Isaac Newton. So, what exactly is the capital F of x? At this point, you must have gone through my lessons, my video lectures about antiderivative. So now, needless to say, this video must be watched after you knew what an antiderivative is. Now I'm going to say where capital F is a function satisfying. See, the best way of saying it, f prime, capital F prime of x equals f. That is a perfect way to indicate that capital F right here is the antiderivative of f of x. That's how useful that is. We don't need to really do any limit work at all. Okay, so this is a theorem. I'm going to step out of the board a little bit. Pause the video if you have to. Take a screenshot if you have to. Take notes if you have to, and have it by your side right here. Because now, after I'm going to move to the other board, we're going to start seeing how valuable this theorem applies for us here. Okay? All right, so let's look at our first example in this discussion here about the definite integral. Let me look at a couple of examples that I have prepared for everyone here. So, example 1, let's get into a straightforward calculation or computational problem. Let's evaluate. So now, our function here is how about x squared plus 1. Okay, that's a function. We want to evaluate the definite integral of this function from 0 to 1. Okay. That's our first problem. So the dx here always comes as part of that integral work, and it does mean it's a thickness multiplied with our function's height. Okay, and we're accumulating all of those products from the beginning point 0 of the interval to 1. So our interval is here, the interval of integration, the interval of the integral. Okay, and so supposedly it's a limit work. Deadly limit work. When I actually teach this material for my engineering calculus students or my formal math major and the calculus students, we have to go through that stage where students feel a little bit of deadliness. But you know, at some point when they start getting in, when they have to leave all that behind and get into the fundamental theorem, they even appreciate a lot more what Isaac Newton has done for us. Okay, but for you guys here, of course, I mean for students who are on track to business field or any of the social or health sciences major, then we don't need to go through all of that experience. It's just for the practicality of your field right there. So, find the antiderivative of this. That's all there is. You don't need any limit work. Find the antiderivative of this. So, well, if you're still a little bit unsure about how to find an antiderivative, pause the video here. Go ahead and open my earlier video when I prepare for any one of you learning about finding an antiderivative. And so now, here's how it works. The antiderivative is first term is a 1/3 x cubed. Okay. Second term is a constant. So it's going to give me 1 times x, which is x. Technically, we will need a plus c. Okay. But I'm going to underline that with a red ink right here because at the very end of this very example right here, I'm going to explain a little bit of that c right there. So technically, that's how we find antiderivative. Okay, and so what I'm introducing here is sort of like a step. So first step is to find. I mean the fundamental theorem of calculus itself gets straightforward into the answer. But see, isn't it obvious that as one step we need to find the antiderivative, and then after antiderivative we do this thing on the right hand side of my theorems right here. Okay, and so now when we're laying it down on paper and pencils as a step right here, then the first step, right after the instruction of the problem, evaluate the definite integral. Then you know we're gonna find as a first step find the antiderivative. But see, after the antiderivative, what will come next? That's why this is sort of like an instruction for what's waiting for us ahead right here. After finding the antiderivative here, we're going to go, see this vertical symbol sign right here means we're going to substitute the found antiderivative here with low n being 0 for x and high n being 1 for x. Okay, that means we're going to have 2 substitution problems to do. Okay, and so it's like I said, that's not the answer yet. It's just one step to get to our final answer. But in this vertical line right here, with a superscript and a subscript here, just indicate that what's going to be the next step after we found the antiderivative. Okay, and so now here's the real work right here. This is our capital F prime. I mean capital F. So now the order as stated in the fundamental theorem of calculus, we need to substitute the upper limit into the function. So now it's going to become, maybe I wrote that a little too close to my ending of the board. So how about right here? 1/3 times 1 cubed plus 1 plus c. Well, it's okay. Let's leave the c there. This is capital F at 1 right here. That's what it is, right from the fundamental theorem of calculus. Okay, and then from that, I'm going to need to subtract the same capital F, the same antiderivative there. I'm going to now need to evaluate that at 0. So 1/3 times 0 cubed plus 0 plus c. This is, ladies and gentlemen, capital F at 0. See, capital F at B minus capital F at A. That's what we're doing. Okay, and so now at this point, we are really ready for just simply doing the next whatever simple math work that gets our final answer. Okay, so allow me to erase this little stuff right here. And so now, I need to also add in another extra comment right here about that c right here. It's an antiderivative. So simply as an antiderivative problem, then you do need to have a c here. But look at the way how our problem is. You see, each one of these need to get a c. Okay, pay attention to that as we go along. So 1 to the third power is 1 times 1/3. So it's a 1/3 here plus 1 plus c. That's for, this is F, capital F at 1 minus, this is 0. That's 0. So that's now just minus c. So it's always going to happen like this. It will always happen like this. Your constants, the constant c in your antiderivative, when we are using that antiderivative for doing definite integral work right here, your constant will always cancel. You got me clear with that? Hopefully, your constants will always, the constant that I mean from your antiderivative answer right there, will always cancel away. And so that's why really, ultimately, you don't need to write that constant in the beginning. Okay, but this thing is only happening when you are finding your antiderivative to do your definite integral. Okay. So now, let me continue. See, all the answer is all sudden just broken down to something very simple. 1/3 plus 1. The answer now is going to be a 4/3. All right. So that's the end of example 1, part A. No limits. Took me 1 step, 2 step, 3 step, maybe into the 4th step to getting that final answer. We didn't see any limits work at all. Easy, and all the big thanks to Isaac Newton that came up and developed that theorem for us, the fundamental theorem of calculus. Okay, so right there, let's stay in this example. We're moving out to part B, and now we're going to start having fun with all of these problems here. So part B. So now, how about our function is x cubed? We want to find the integrals from -1 to 1 of our, see, our interval is from -1 to 1. The function here is x cubed. Okay, so let's find the answer. First step to get nailed down, find the antiderivative. So antiderivative for something like that is a 1/4 x to the 4th. And now, as I said earlier from the earlier problem, part A, now we no longer need to have the plus c here because it will get canceled out. So that's all we need. We only need to get the core antiderivative, the main antiderivative. And so now the instruction for the next step, we're going to need to, from here, substitute in the two values low and high of your interval. And then from there, fundamental theorem of calculus says that antiderivative there is going to be substituted evaluated at the upper end. Okay, and then from there I'm going to subtract 1/4 times -1 in parentheses to the 4th power. All right, and so the answer we're looking at now is going to be a 0 if we're doing the math properly. Okay, and so now we are, and you see how much I have picked up pace right there, and you've seen all that repeated steps and just apply on a different function with the different intervals. That's all. But the work here is fabulously done, all thanks to that fundamental theorem of calculus. Okay, and so now, how about another problem? For part C of our current example. So, what about in part C here, we want to evaluate with our function here being e to the x, we want to evaluate the integral from -1 to 1 on that function right there, e to the x. Okay, and so again, let's see how easy this is. Antiderivative is always the first step, e to the x. And just like I said, we don't need the plus e here when we are finding antiderivative to eventually find a definite integral. So we don't need plus e here, but attach that instruction to indicate that the next step now is to evaluate the two upper end and lower end values there. Okay, so now we are ready for the next step. The next step now is from where that antiderivative, I'm going to substitute in upper end first, then subtract. Okay, the same antiderivative there, but substitute it in, evaluate it at the lower end. Okay, and so this is just e, and when it comes to e, I tend to keep just the exact expression rather than going 2.718 or whatsoever. Okay, so this is e. E to the -1 power is really 1 over e algebraically, so minus 1 over e. You can leave your answer like that, or I can also recommend making common denominator. Now it's just the algebra to re-express your final expression. So making common denominator, we can land into e squared minus 1 over e. It's a different way of expressing your final answer. Either way, it's just fine. I'm just staying away. First thing, I don't have a calculator up here. And other than that, it's just my favorite choice. I leave these answer that involves e in exact expressions. Okay. And so now that's what we've had for the whole example 1, but hopefully it already gave viewers and students of mine a broad view of the, how useful that fundamental theorem of calculus is. And see, none of the problem we've done so far required me or required you to go through the limits at all. And so have fun with this and start enjoying a lot of either you are my students or you are viewers. I'm pretty sure as you're learning on this video, you will be exposed to different problems. Start enjoying the usefulness of this fundamental theorem of calculus. Okay, and see how fast the speed of your work has become. Okay, and so now as we are done with that first example, the definition, the fundamental theorem of calculus is here, and then let's talk a little bit more as far as the details of a definite integral, so that we can be clear here. So fundamental theorem of calculus is just the tool, the methods to really evaluate any definite integral. But ultimately, again, the integral itself is accumulation, and I brought it up. I brought that up in the earlier discussion of this video here. And so now I have to be clear again. Even though I keep using an area as a demonstration, but now I have to be clear. See, now you have a function, and we want to, as a verb, we want to integrate the function here over the interval from a to b. Or as another way of saying, we want to take the integral of this function over the interval from a to b. And this is now a definite integral because it has a low end, a definite low end, and a definite upper end right there. Okay? But so now I have to emphasize again. A definite integral for whatever function that is over a given interval is not, okay, it's not exactly the area. Yes, I admit it's the only way any instructor starting out to explain for their students how useful an integral is to bring up an area. But at some point, that instructor must point out clearly, and including me, I must point out clearly for any of my students, ultimately an integral itself, a definite integral, is not exactly an area. It's not exactly the area specifically, because over time explaining, then some students may attach any integral with a picture like this. You got a curve, f of x, and then inside of that curve, we got an area between the curve and the x-axis, and then the interval from a to b is here, and because, see, functions, f of x here is the function's height at any instant x, just like how I've been explaining, and then each of the stripe here has a thickness dx. See, the thickness of that pencil stripe is dx. So the functions, so f of x is the height multiplied with the thickness. That gives me you can think about it as an area, but see, now I'm trying to make you understand that it's not an area in the sense that, look at our result in example 1 just now, but part B. Look back at that. Feel free to roll back on my video and have a look back at it. What was the result there we've had? Our integral from -1 to 1 on that function was the function x cubed. Okay? And look at what answer we had there. 0 as the answer. So why was that? See, because if we permanently tie our mind down to an area, an integral has to be an area, then we, as I explained earlier, we are permanently stuck with the idea that an integral has to be a positive, because the area is positive. But nope, it's the integral originally came out just as a definition. It's a Riemann sum. Okay, it's a Riemann sum. And then on top of that Riemann sum, we are taking limits for n going to infinity. And so that's why in that case, see, back to our Riemann sum discussion, I made it clear, really clear, that Riemann sum on its own is an operation. So Riemann sum was not necessarily itself to achieve an area. We use Riemann sum as a tool to find the area. But Riemann sum on its own is not an area. So now an integral is the more advanced version on a Riemann sum. The Riemann sum where we're going to let n, the number of subintervals, increase to infinite. And so in that way, just like that, an integral is a tool to find the area, but it's not really an area. It's not exactly an area. Okay, so why is it that in this problem right here we got an answer of 0? Because think about it. See, each stripe right here is a product. We make a product between the function's height with the thickness dx. So thickness is true. It's always having a thickness. Even a pencil stripe like this has a thickness. That's dx. But stripe, it could be, your function could be up and down like this through the x-axis. So maybe in some intervals where your function is negative, who knows? Then the height of the function is actually a negative height. That height can be negative. And so multiplying a negative height with that, so we just have a negative product. And that's why it's a best tool to use to approximate area, to find area, to find exact area, but it's not necessarily means any of the area. So my main aim, for back to example 1 that we just now finished, my main aim here is to get any of you, the viewers or my students, to be comfortable with using the fundamental theorem of calculus. But as you were working along your way here and outside of this video lesson, go ahead and dive into any of the standard calculus textbook, pick a problem and get it done. But I want you to do those problems that completely in the back of your mind leave out the area imagination. Or it doesn't hurt that you imagine it as an area, but be ready to accept that the answer there might not be consistent with in the way you think that it's an area. Okay, because area, in the way we think, we're always going to have to end up with positive area and some physical viewable amount. But for example, part B that we just did here, it was a 0. So now, directly let me explain why in that particular problem it was a 0. So how about, let's bring it on the graph right here. Let me quickly prepare my computer screen and let Desmos answer that for everyone. All right, so let's bring up the actual picture now. All right, so here's our famous graph for x cubed function. Okay, and so these two tick marks right here are to indicate that's my interval from -1 to 1. That's example 1, part B in this lecture right here. And then, see, if we're looking at the area, so now doing the integral work, then we're going to have See, left area or right area, they all agree to the same exact amount. They all agree to the idea that as accumulations, all of these accumulations being the negative accumulation. So let me zoom it out a little more. All right, so the accumulation that we created through the integrals will give us some negative. So from negative 1 to 0 over here, the accumulation all became a negative accumulation. And then after the function switched to the positive side here, when x is positive now, then the accumulation became positive. And now as far as the symmetry of the curve itself right here, then the negative accumulations will cancel nicely with the positive accumulation. And because, again, as I said, an integral itself has never been really an area. So if we really are approaching this as an area problem, then we need to treat that eventually as a positive amount and add with the other positive amount, and we have a double. But now that will come in the next example. But here, the reason we have a total 0 for our integral is simply because the accumulation on the left here is a negative amount for whatever that was. And then this other accumulation is the exact opposite sign. And so adding them up together, it was a 0. Okay? And so that's the reason why. And the same with the right Riemann sum with infinitely many accumulations, with a lot of accumulation, with a very high number of subintervals already. Okay? And so that's the reason why I was just now explaining that an integral, a definite integral, is not an area. It's not the area. It's not. And when I'm saying the area, I meant the area of this function with the x made by this function with the x-axis in between a and b. It's not necessarily that. It could be the area that sinks below the x-axis. So in that way, now I break away your understanding about an integral. A definite integral is not an area. It's not the area. Then what can we see that as? So you can have the following interpretation, which is just fine. And right along with that picture illustration I brought on the computer screen earlier, then now we can understand an integral over the interval a to b right here of a function f of x. It's not an area, because area has to always be a physical area being always positive. Okay, but this is, we can understand this as the net area. How's that? Okay, the net area, because now when you're drawing graphs right here, some area of the graph sinks below the x-axis, negative area, some other area of the graph stays above the x-axis, jumped above the x-axis. And so this total accumulation is the net area. That's how I want you to see it. Just like a net amount in your bank account. Some month you will spend more than you earned, right? Then your net amount is negative. Some month, some other time, your spending is equal with your earning. You got a 0 amount, net balance right there. And then in some other month, your earning is more than your spending. You got an overall the positive net balance. So as far as the function's area, we also have that concept of net area. Okay, so it's a net area, of course, between the function f of x and the x-axis. Okay, and then from x equals a to x equals b. That's the best way of understanding what the definite integral is. It's a net area. So again, just like on the picture I was describing here. See, the whole total accumulation is a net area because there's negative area and together with the positive area. So net area is a 0 balance, 0 net area. All right. And so that's what it is regarding these kind of problems right there.